Hello and welcome to EE323, Lecture 7. Today I'm going to be talking about a number of topics, including Zener diodes and the application of Zener diodes in a circuit called a voltage regulator. I'll introduce a new type of circuit called a clamping circuit, and then I'll finish the lecture with a brief discussion of special p-n junctions. You can find this in your book in sections 4.3, 4.5, and 4.7. Okay, let's get started. So first of all, up to this point in the class, we've really been focusing on the IV characteristic shown in the upper right here, which is the forward biased exponential current voltage relationship. And there's another region of operation actually in reverse bias, and up until this point, we've been thinking of reverse bias as having very little current, which is true. But if the reverse bias voltage gets large enough and exceeds a certain threshold, then we get something called breakdown, and we can actually get a large negative current. The breakdown can occur for a number of reasons, including tunneling or avalanche breakdown. As long as we keep the current limited so that the current doesn't get too high in the negative direction, this actually won't damage the device permanently. So we can use it in this reverse bias region. And so this is a new, we model this, or we call this a different type of diode when it's operated in reverse breakdown. And this is called a Zener diode or breakdown diode. And the symbol is slightly different. Notice the symbol, it's like the diode symbol, but it has these little arms on it. And so when you see that, you'll know that that's the circuit symbol for a Zener diode. And if we get into the IV curve a little bit more closely, this is what we see. First of all, we're only looking in the reverse bias region here, right? And the current stays pretty low until we get to a voltage, which is approximately called the knee voltage here. That's what this VZK stands for. So V Zener, the knee voltage. And that's kind of about the voltage where the diode will turn on. Now, once the diode is on in this reverse bias region, we can see that the current voltage relationship in this area is nearly linear. And so we approximate this for circuit applications. We approximate this as linear, and the slope of that line would be 1 over RZ, where RZ is the Zener resistance. And now if we take the intercept with the x-axis, we come up with this value of this straight line, this value VZ0. And then finally, VZ would be, if this is our operating point, for example, that would be the voltage at that operating point. And then there's an associated current at that operating point. And this RZ, we can think of it as an incremental resistance. It's usually pretty small, on the order of tens of ohms or single ohms. So in other words, this line is very steep and the current changes very rapidly with a small change in voltage. Okay, so if we want to model this, right, one thing we notice is we can notice that this VZ0, which is the x-intercept of the linear approximation here, is very close to the VZK, which is the knee voltage. And so if we approximate those two as say they're approximately equal, then we can write an expression for this line where we sort of linearized, sorry for the squiggly line, it's meant to be straight. We've linearized the IV curve here. And what we see is if we write an expression for that line, we can see that at some voltage, VZ, we have the x-intercept. In that case would be VZ0, and we can represent the voltage as a function of the resistance RZ and IZ. And if we assume that is assuming that IZ is greater than IZK, that is, and VZ is greater than VZ0, that is, we're in the breakdown region. If we're operating over here somewhere before the breakdown region, this equation here does not apply. And so in the breakdown region, this corresponds to a fixed voltage, VZ0, along with a series resistance, RZ. So this is the circuit model that we'll use for the Zener diode. assuming this is a linear equivalent circuit model. And this is what we'll use when we try to analyze circuits with Zener diodes in them. Okay, so what circuit might be of interest to us that might take advantage of these characteristics? One thing I should note about the Zener diode is that this VZ0 or VZK, where the breakdown starts to happen here, it can be adjusted for different diodes. So it can be set by the technology. So we can adjust it to 5 volts or as high as 20 or 30 volts. This breakdown can really change depending on how the diode is fabricated. So that gives designers a lot of latitude when they're choosing this as a device. So where might you use this? One example is a circuit called a voltage regulator. Now, a voltage regulator essentially takes a DC, close to DC signal and creates a very smooth, different DC value signal at the output. So one example, as I show in this image here, is that suppose we have an Arduino board and we're trying to power it with a 9-volt battery. The Arduino would like 5 volts DC, not 9 volts. So we can use a device here called a voltage regulator to convert the DC level from 9 volts to 5 volts. And it will also reduce variation from the source. So if our battery voltage, say our battery voltage where it's kind of squiggling around like this, then hopefully in the center of that was at 9 volts, then hopefully the output of our regulator would be very constant at 5 volts. That's the goal of a voltage regulator. And so how might a Zener diode help us with this? Well, here's an example of a pretty simple circuit that takes advantage of these Zener diode characteristics. So we have a supply, which in this case is called V+, mean value of 10 volts, with one simple resistor, and then a Zener diode. And what we can see is that as long as this Zener diode is on or in this reverse bias breakdown regime, that the voltage across the Zener diode stays very close, in this case, to 6.8 volts. So in this example, the value of the Zener diode is 6.8 volts, and that's at a current of 5 milliamps. And for this particular diode, we're going to assume that the incremental resistance, which models this as a linear circuit, is 20 ohms. And the knee current associated, that's the current associated with the knee voltage, is 0.2 milliamps. So what I'd like to do is use this diode to regulate a DC supply that's given by V+. That is, it's 10 volts, but it has a plus or minus 1 volt variation. So it averages to 10 volts, but it's not highly regulated at 10 volts. It has a fairly large variation of a volt. So we'd like to use this to make a DC voltage with much less variation. And so if we want to characterize this, right, we can characterize the output, the variation in terms of how much the output voltage, which is this voltage right here, varies as a function of the supply variation. So if we divide the output voltage, the change in the output voltage for a change in the supply variation, that's what we call the line regulation. And we can also determine something called a load regulation, and that's how much the output voltage changes if we have a change in the load current that would be flowing through this load RL. So we'd like to determine both of these with this specification that the load current is nominally 1 milliamp. And then the last thing we'd like to determine is, will this work if the load resistance goes down to 0.5 k ohms? Okay, so let's get started here. And the first thing we're going to do is replace the Zener diode with our equivalent circuit, our linear equivalent circuit, which has a fixed DC voltage, VZ0, and a resistance RZ. And if we do this, we can determine that VZ, right, the output of our Zener diode, is equal to VZ0 plus RZIZ. And in this case, this would be 6.8 volts is equal to VZ0 plus RZ, which is 20 ohms, and we know that the current is 5 milliamps. And by just applying the simple equation, we can determine what VZ0 is. In this case, VZ0 is equal to 6.7 volts. So VZ0 is 6.7 volts, but with a current of 5 milliamps, that gave us a 0.1 volt drop across the resistor. So our total at the output was 6.8 volts. All right, so that helps us find VZ0. Let's move on. We can now find the current IZ through our diode. So how would we do that? Well, we can write that IZ is equal to I, right? There's no load connected in this example so far, which is going to be equal to V plus minus ground, so that's just V plus, minus V0 divided by the total resistance. So it's the voltage drop divided by the resistance. So that would become V plus minus VZ0 divided by the resistance, which is R plus RZ. And so that's going to be equal to 10 volts minus 6.7 volts divided by 0.5 k ohms and plus 20 ohms. So if we do that, we can solve for IZ, and that's equal to 6.35 milliamps. And with that, we can determine what the output voltage is with no load connected, right? And we can, so this is essentially like an iteration here. We can say V out is equal to VZ0 plus IZRZ, which is equal to 6.7 volts plus 6.35 milliamps times 20 ohms. And that gets us to VO is equal to 6.83 volts. So the earlier assumption that this was 6.8 volts based on IZ of 5 milliamps wasn't quite right, because the current was actually, as we determined the current was a little bit higher, and hence this is now 6.83 volts when there's no load at the output. Okay, so now if we want to determine the line regulation, we need to determine the change in V out, right, for a change of plus and minus 1 volt in the supply. So if the supply were to change by plus or minus 1 volt, how much would the V out change? Well, we can write that the change in V out, right, this is just going to look like a resistive divider now, because this is a constant, and so all we have is a resistive divider between RZ and R. So that would be that it's the change in V plus times the across this resistive divider, which is RZ over RZ plus R. And so that's going to be equal to plus or minus 1 volt times 20 over 20 plus 0.5 k ohms. And that tells us that delta V out is equal to plus or minus 38.5 millivolts. And so for the line regulation, we would actually divide these two, delta V out over delta V plus, and that's the same thing, and that's equal to 38.5 millivolts. So what that tells us is that if their supply voltage changes by plus and minus, it should be plus or minus, if our supply voltage changes by a volt, our output voltage of this regulator changes by plus or minus 38.5 millivolts. So it's way smaller, right? Much smaller. And that's the action of this shunt regulator. That's what the regulator is doing. By the way, it's called a shunt regulator because the load here, this RL, is in parallel, or it's shunting the diode, the Zener diode. Or you could say the Zener diode, the regulator is shunting the load. Okay, so that gives us the line regulation. And now we can move on and determine what the load regulation is. That is, if IL is equal to 1 milliamp, right, how much does the voltage at the output change? So in other words, you have a load here, suppose it's a charger of some or a cell phone or something, and you have it off, it's consuming very little power, and then you turn it on, and now it's consuming a milliamp. How much does the voltage change? And so now the current IZ is going to be 1 milliamp less because we're getting a milliamp to go through the load. So again, we can determine what the change in voltage is through this resistor RZ. And so we can say that delta V out is equal to the change in IZ, the change in the current flowing through our Zener diode, times RZ. And so the change will be minus 1 milliamp, so we're getting 1 milliamp less, times 20 ohms, and that tells us that delta V out is equal to minus 20 millivolts. So we could write then that delta V out over delta IL is equal to minus 20 millivolts per milliamp. So that tells us that if we increase this from 0 to 1 milliamp in our load, we only get a 20 millivolt change in our output voltage, which again is pretty small, and it's doing a good job of regulating the output voltage independent of how much current is being drawn into the load. Okay, and so for the last part of this problem, let's assume that RL is 0.5 k ohms. Is this still going to work? So if RL was 0.5 k ohms, we could write that IL would be equal to V out over RL, and that's equal to 6.83 over 0.5 k ohms, which is equal to 13.7 milliamps. Now, we had previously found that IZ was 6.35 milliamps for V plus equal 10 volts. And this is going to, if this voltage stayed at 6.83 millivolts, this would be 13.7 milliamps. And so there's a problem there with how much current can be redirected from the Zener diode into the load, which makes us think that maybe this diode is actually not far enough reverse bias and not in breakdown. So if we assume that it maybe wasn't in breakdown, right, in other words, the diode's not conducting, then we'd have a simple voltage divider between the load resistor, the source resistor R and the load resistor RL, and we could write that V out in that case is equal to V plus times RL over RL plus R, and that would equal 10 volts times 0.5 k ohms over 0.5 k ohms plus 0.5 k ohms, which is equal to 5 volts. So clearly this voltage at the output is now not high enough to break down the Zener diode, and the Zener diode is off. And so our assumption was correct that this couldn't happen and that this is no longer being regulated by the Zener diode. Okay, let's move on to a different application, a different circuit involving diodes. This is involving a traditional diode. This is called a clamping circuit. And what a clamping circuit does is it's used to restore DC values to circuits. So sometimes the DC value gets lost. And this often happens if you pass a signal through a capacitor, you have some V in, suppose that's got some AC and some DC associated with it. At the output, you're only going to get the AC because DC can't pass through a capacitor. So this is often a problem in communication, so you want to restore this DC value to an AC signal. And here's a circuit that will do that. It's very simple. You have your input value, which is the AC value without the DC, and you have a diode and a capacitor. And let's see what happens here. That intuitively, what should happen when our input goes low, right, then we're going to charge up the positive side of the capacitor through the diode because it will be forward biased. But the opposite can't happen, right, because in reverse bias, no current will flow. So this voltage will get stuck. And so what happens is when the input voltage is low, the output, this input voltage is low. This output voltage charges up as high as it can go through the diode, which would be at 0 volts. And now when the input voltage switches back high, right, then what we see is that the voltage across the capacitor switches up by 10 volts because no current can then flow back through the diode and discharge the capacitor. So essentially this gets shifted up by this lowest value here, and so that essentially it gets shifted up by 6 volts because of the action of the diode. And so you can see how the diode is clamping this or shifting it up. If you switch the diode around, you can clamp it on the negative side and move the waveform down. And so this is a way to reintroduce a DC value into an AC signal. All right, so moving on, we're going to talk about some special types of PN junctions. One that you'll hear referenced fairly frequently are called Schottky barrier diodes. These are a little different than PN junctions. We normally think about a P-type material and N-type material. Schottky barrier diodes happen when you put a metal next to an N-type material, as opposed to a P-type material next to an N-type material. And the symbol is, again, slightly different here. It's very similar. The behavior is very similar to a PN junction. They tend to be very fast switching times, and they tend to have a lower forward voltage drop, which can be useful in certain situations. And they also have a very large saturation current. So they can flow a lot of current with a low voltage drop, but still have the diode-like behavior. So you'll hear this referred to as Schottky diodes or Schottky barriers. Another type of diode is called a photodiode. Now, this little simple picture here at the top just shows the light coming into a diode. And essentially what happens is, as the photons from the light hit the semiconductor, they're absorbed by the semiconductor, and they create an electron-hole pair, right? So they break this apart and create a free hole and a free electron. Now, in the presence of the electric field, and when this is reverse bias, the hole gets swept to the right, the electron gets swept to the left by the electric field, and we end up with a current coming out, and that's a photocurrent. And so this is used in optical communications or whenever you really want to detect light. And so essentially what happens, if you look at the IV curve, keep in mind we're operating in this reverse bias situation where we have this depletion region with the electric field to allow the electron in the hole to get swept out. So the current is negative because we're operating in reverse bias. And so when it's dark, we follow one IV curve, this dark IV curve. And then when it's light and we're creating these extra electron hole pairs, the current is more negative, and we get this increase in negative current to detect the light, essentially. And this photocurrent is proportional to the light intensity. So the brighter the light, the more current you get. And another application of the same effect is really a solar cell. So in this, with a solar cell, you don't reverse bias it, you just hook up a load to it. And again, but you would have a depletion region, right? And again, when the light comes in, it's going to generate an electron hole pair, and the hole is going to get swept out, and the electron is going to get swept out, and it's going to create a voltage across this resistance, just in the same way that the photodiode did. This is essentially how all photocells work. There's a lot of detail that goes into the materials to optimize the chance that a photon is actually going to generate this electron hole pair, because most of the photons that hit the semiconductor will not. So you try to increase the likelihood of that happening through careful engineering, material engineering. Okay, and the last type of diode I'd like to talk about, special diode, is called a light-emitting diode, or LED. These are used very commonly today. And essentially what happens is that now this is a forward bias situation. Notice it's forward bias. And when the when the minority carrier holes and minority carrier electrons get injected across the barrier, there's some recombination that goes on. And during this recombination process, at least in certain types of semiconductors, photons are created. And this does not happen in silicon. We need what's called a direct bandgap semiconductor, which is not silicon. So other semiconductors are like gallium arsenide, gallium phosphide, gallium nitride, and these are direct bandgap semiconductors, and this recombination leads to a photon coming out of a certain frequency or a certain color. And so depending on the semiconductor and the bandgap we're dealing with, we get different colors that are emitted from the LED. And so this light intensity is going to be proportional to the current, because the more charge carriers you have, the more light you get, the more recombination you have, and the more light you get. Okay, and that is it for this lecture. Thank you very much.